Good morning. Good morning. Yeah. So I'm glad to have this opportunity to tell you how much I enjoyed the talent show last Friday. I'm always amazed at the talents of Cosmos students, especially some unexpected ones. Yeah. But this is the last week of Cosmos, right? So you are very busy, too busy to feel sad, right? So today is the last discovery lecture, and today's and last Tuesday's discovery lectures focus on nanotechnology and its applications to several important areas. And we are in for a treat, as you shall see. It is a pleasure for me to introduce Professor Michael Saylor of the Department of Chemistry and Biochemistry here at UCSD. Professor Saylor's group focuses their research on synthesis and study of nanophase materials with unusual optical, magnetic, and electronic properties. Current research focuses on problems that are based on nanoparticle-based diagnosis and treatment of disease, remote sensing of pollutants and toxins, and point detection of, for biological or chemical warfare agents. Yeah. So Professor Saylor graduated with a bachelor degree from Harvey Mudd College in chemistry and obtained his PhD in chemistry from Northwestern University. He then worked at Stanford and Caltech before coming to UCSD in 1990. So he has garnered many awards and of course, many journal papers, and he has 28 patents or patents pending. And I'm particularly impressed that 21 of these 28 patents have been licensed by established or startup companies. So it's very innovative. Yeah. So let us welcome Professor Saylor. Yeah.
Good morning, you guys. So we were just comparing notes before my presentation today. I guess I've been running a summer program as well. I had about 10 high school students in my lab this summer, and I called it Summer School for Silicon Nanotechnology. And I'll talk to you a little bit about some of the highlights of work that was going on that led up to this summer, but I'll try to touch on a couple of experiments that the students are working on. Those kids are mostly coming, like you, from California high schools, but focused on just the San Diego area, and it's only 10 of them. It was a much smaller program. But it really illustrated to me how important it is to try to do this kind of activity with people at your age. I hope you guys have had a good summer. And you got exposure to some interesting topics and concepts, I hope. Today I'm going to be talking about nanotechnology. And I think I'll start out with this picture here. So I'm not sure if anybody is familiar with this. I don't have a lab, do I? I'm going to have to stay here. I like to walk around, but if I walk around, I'm going to have to yell, I guess. So, okay. So can anybody tell me where the nanotechnology in this picture? This is Of course, this is a website from Gore-tex. Okay. What about this one? This is another website. This is from a drug company that makes a drug called Abraxane, which is an anti-cancer drug. It's actually quite effective against in treating breast cancer. This one is probably the most easy one to pick out. Can anybody tell me where the nanotechnology is here? If you can read, you can see it. Okay, so all three of these have examples of what we call, what we refer to as nanomaterials, and generally deriving out of an area called nanotechnology. If you can't read the French, it's written there in English, and this is a cold cream that has nanoparticles made out of gold. Okay, so what what do all those things have in common is they all have something that derives from a nanostructure in them, and we're going to talk about all three of those examples in a few minutes. I want to start with this slide here, just to get my test out of the way early. This is supposed to be an educational activity, and so I need you guys to take the test. How many people want to vote for A here? All right, good. Yep, that's right. Did you guys go kayaking or swimming last weekend? It is deadly if you fall in and you can't get to the surface. What about this one here? What about this one? Okay, number D. These last three get kind of hard because these are chemical formulas and we really don't know what they are just by looking at them. But the top three are ones that you can, as you probably all figured out. This, of course, is water. What's Fe2O3? What? Iron oxide, very good. Otherwise known as rust. It's one form of iron oxide. There are a couple of different forms of it, but this is one of the most common. SiO2, of course, is silicon oxide. That's glass, window glass or beach sand. This one turns out this is the formula for aspirin, so that's not the deadly chemical. This next one is strychnine. Does anybody know what that is? You guessed it in the back? You figured it was strychnine? Good for you. Yep. Okay. What does it do? You want to tell me with your thumb up in the back? Anybody know what strychnine is? Rat poison. Rat poison. It gets into the little rats and mice eat it, and it causes them to bleed to death internally. So it's like a bad chemical. This is toxic. This last one is chrysotolite. Turns out this is a mineral you dig out of the ground. And so I guess the first part of the lesson is that, between these two, if you're taking the, an SAT, or some of you have probably taken, anybody taken the PSAT yet? You guys taken some of those? So, the first thing you learn is you look for the most complicated answer, and that's probably the right one. So if you got to guess, you may as well take the last one here. And you would have been sort of right. These two both are deadly. Just by looking at these chemical formulas, you really can't tell what's going on here, though. What makes this aspirin, cure your headache, whereas this strychnine, okay, it's got a carbon, hydrogen, oxygen, and a nitrogen in there. A little bit different formula, but it's really how those atoms are put together that makes it so bad. That last one, chrysotolite, is otherwise commonly known as asbestos. So you've seen these commercials or heard on the radio the ads for the if you have mesothelioma, you may have been exposed to asbestos, and you can sue your former employer for millions of dollars. What they're looking at, the reason that people don't like this material is it's sort of everywhere. Back in the 50s and the 60s, they made ceiling tiles out of it, put them in the roofs of buildings and put them in the walls, and made fabrics and clothing out of it. Why is it so bad? It's actually, if you look at the chemical formula here, it has a lot of the elements of those other compounds we were talking about earlier. Na, that's sodium chloride, that's pretty harmless. Fe2O3, there's that iron oxide. There's another form of iron oxide. SiO2, that's silica. And so it's really not the chemical formula. There's no plutonium in asbestos. The reason it's so bad is you breathe these little fibers of this mineral into your lungs. That's what they look like there. And they get into your lungs and they don't go away. They stay there for decades. In fact, the people who have this disease, mesothelioma, they'll find that they were exposed to this material maybe 20 years earlier, and they'll go into their lungs and they'll actually find traces of these fibers still in there. And what happens is the fibers get into the lungs and they create, they basically poke and scratch at the cells and cause them to die, and eventually they have to regenerate, and as they keep regenerating, eventually they mutate, and then you get the disease. And so it's really not the chemistry so much as it's the form, the shape. In fact, if you breathed in or ate, any of these some other compounds made out of any of these formulations, they pretty much be harmless. But for some reason, these little fibers get stuck and they don't go away and they don't dissolve. And so, although toxicity in materials can often take the form of chemistry, like the strychnine, the form of the material and how much you're getting, the dose, where it's going. So In fact, if you were to rub your hands on asbestos, you would probably not get sick. It's just the fact that it gets into the lungs in this case. And the availability. And so if you've got it everywhere in the environment, or you're putting it on your roof and making solar panels out of it, for example, maybe it'll be a problem in 20 years. And really, this is one of the first lessons of nanotechnology. This is a nanomaterial, right? It's a little fibers, a few nanometers across. It's a natural nanomaterial. You dig it out of the ground. It's not man-made. However, you know, when they were making ceiling tiles out of these things in the 50s and putting them in people's houses, they had no idea that this was a deadly material. In fact, it was really a helpful material because it's a rock. If you make a ceiling tile out of wood, when the house catches fire, you know, people burn down, and that's not good. So this was like a lifesaver, you know, when they first were using this material, and that's why they used it. And it took them 20 years to figure out that there was something wrong with it, actually more than that. And so that's one of the first lessons, is that if you're going to be making a material and it's going to go everywhere, you really often don't know the consequences for many years. So that's the starting lesson for nanotechnology, and that really wasn't what Richard Feynman was thinking about. How many people have seen this, referenced this before, or heard of the Feynman lecture? There's a set of notes called the Feynman lectures, which are, of course, physics lectures. But he took his time off of being a physics professor at Caltech one night, and he went and gave a dinner talk and to the American Physical Society. And this is a quote that comes out of that talk that he gave. And he was looking at that time. This was put out. He gave this talk in 1959. And at that time, they were making tools that could allow us to see things really small. Electron microscopes were just coming of age, and they also were starting to just develop the concepts and the ideas and the understanding of how cells work in biology. And he looked at these small machines in the body and in animals and in plants and said, wow, if we could make something like that and have it make chemicals for us, or have it convert sunlight into some fuel, we'd be able to do a lot of things that nature doesn't really want to do, and maybe we'd be able to make something useful. And so that was really where this lecture came from. It turns out, keep track of that, okay? It's 1959. So there's another form of nanotechnology that I like better. How many people have read The Cat in the Hat? How many people want to admit they've read it? This is The Cat in the Hat Comes Back. It's one of the many sequels that he wrote. This is in particular one of my favorites because, of course, as most, I'm sure you know, Dr. Seuss was Ted Geisel. Our library is named after that guy. He spent many years in La Jolla. And so in this story, there's this cat, Cat in the Hat, that's his hand there, and he takes his hat off, and standing on top of his head is another cat, and it's about half as tall as him. And then that cat takes his head off and so forth, and then that's how they make all these little cats. And so if you assume that the Cat in the Hat is the first one, and then the cat on his head is Cat A, and that cat is half as tall as the first cat. So the Cat in the Hat, let's say he's 6 feet tall. Cat A is 3 feet tall. Cat B is 1.5 feet tall, and half so forth. How big is Cat Z? Anybody want to tell me? Get your calculators out. What? A nanometer? That's just because you know the context of the lecture. You're pretty close. Yeah, the answer was a nanometer. Anybody figured it out? Anybody want to tell me the formula, how you figure that out? Come on, I gave this lecture at La Jolla High School a few months ago, and I had 3 kids in the audience who knew how to do the calculation. Yeah, you with the hand up. Yell it out. This is why I need a laugh. What did you say? No, too complicated. Over here. Yeah, the yellow shirt. That's a lot easier formula. That's the formula I was looking for. In fact, that's right. So the Cat in the Hat, if he's 6 feet tall, maybe, I'm not sure. You can calculate your formula, and you probably just have to do some algebra on it and get the same one. I don't know if you got it right or not, but the one I was looking for is basically you just take 1/2 each time the cat gets cut in half. and you raise it to 26 power. 26 is the number of letters in the alphabet. And if you do that calculation and you convert to nanometers, it turns out you're not too far off by a factor of 30. I'd take that as I'd give you full credit for that one. That's 27 nanometers. So actually Dr. Seuss figured out nanotechnology way before Richard Feynman, because Dr. Seuss, this book, The Cat in the Hat Comes Back, was published in 1958, 1 year before Richard Feynman's famous lecture. And what's the most important thing about this is that he figured out that you could make something really small and have it do something that a big cat couldn't do. And in this case, it clears up this pink stain that's on the snow outside the house of the kids that the Cat in the Hat made. Okay, so now Gore-tex. Where's the nanotechnology in Gore-tex? If you go to their website, by the way, Gore website, it doesn't say the words nano anything anywhere. It's thought at least in terms of marketing strategies, there's no need to tell people that they're wearing nanotechnology. Maybe they'll be scared by it, so let's not tell them. In fact, nanotechnology is probably one of the original, Gore-tex is probably one of the original nanotechnology materials. If you go back, it was actually invented back in 1985, so before a lot of you guys were born, probably. And what is it? It's this fibrous material with little holes in it. And it turns out, this is my cartoon of how Gore-tex works. Water drops, like when you're outside wearing a Gore-tex jacket or boots, that's a fabric that they make that's water repellent. The water drops hit the surface, and it's a reasonably, kind of plasticky material, and so the water doesn't soak into it, and also the droplets are too big to fit through those small holes. The holes in Gore-tex are about 200 nanometers. And it turns out the water drops can't be made that small. The surface tension of water is too great, and if you try to squeeze a water drop down to being that small, the radius of curvature is just too tight, and the water drop will actually spontaneously evaporate. And so liquid water will hit the surface, and it just can't squeeze through those holes. Its surface tension is too great. And so when you get rained on in this thing, it just bounces off. However, water vapor, the molecules of water, are much smaller than liquid drops. And they're, in fact, much smaller than 100 nanometers, and they'll just zip right through those holes. And so the beauty of Gore-tex, really, is that, if you wear it, you could wear a plastic bag and not get wet when you go out in the rain, but then you're going to start sweating, and then you'll just get all clammy on the inside, because your body, if you take your socks off right now, any of you guys, you probably couldn't wring them out, but after walking around outside, there's a lot of water in them. There's a lot of water in your clothing. Your body is putting out a lot of water just sitting there. And so this water naturally goes through your clothing, and it goes through Gore-tex just the same way. But unlike the cotton T-shirts you guys are wearing, the liquid water, in the case of Gore-tex, will not go through. So it breathes, so the liquid water, or the vapor that from your sweat and so forth, just gets right out, so you don't get clammy, but the droplets don't get in. And so this is probably the first example I want to give of what is nanotechnology, and this is a very good example of it. Now, why is this nanotechnology? What if you made the holes bigger? Okay, let's just perforate it, make it like a cotton shirt or something, or a poly shirt. Of course, the holes are so big that water will go right through that. Liquid water will. If the holes are too small, then it's like wearing a plastic bag. Even the liquid water won't go through, but the water vapor won't go through either. And so that hole has to be in this kind of key size range. It has to be about, in this case, about 200 nanometers. So if the pores are too big, you get wet. If they're too small, you get clammy. And so the 200 nanometer size scale is nanotechnology. It's a property of the material that derives from a size, a characteristic size, and that's what we mean by nano. So this is also a nano object. Turns out this is the aspirin molecule we had in our quiz a few minutes ago. This is a chemical molecule. It's about a nanometer across, and the reason that I would say this is not nanotechnology, and now chemists make these things for a living, right? We make molecules. That's what a lot of us do for a living. Why is this not nanotechnology? It's the right size. It's your 1 nanometer size there. And the reason it's not is because if we take this molecule and we pull off one hydrogen atom from that CH3 group, or we take this oxygen atom away, we remove one atom, and this molecule becomes something else. And it probably won't cure your headache anymore. It may get you sick. It may just not work at all. And so molecules really require a very specific chemical structure, and it's not their size that counts so much. It's just how those atoms are put together. And in the case of Gore-tex, you know, if you made the holes a little bit bigger, maybe 250 nanometers, or a little bit smaller, maybe 150 nanometers, it would still work. Okay, so it's not critical to have exactly that structure, and in chemistry it is. So this is a second example of a nanomaterial I want to talk about. This is a so-called quantum dot. How many of you guys, did anybody work with quantum dots this summer? Anybody do anybody know what a quantum dot is? Okay. So this is made from two elements, cadmium and selenium. This is a so-called precipitation reaction. You mix these guys up in a water beaker, and they combine and they form a small crystal. And this is a small crystallite of cadmium selenide. The reason we call it a quantum dot, before we get to that, just to give you an idea of the size here, this is the aspirin molecule. So it's a little bit bigger than an aspirin molecule, but this is a nanostructure. The reason we call it a quantum dot is given in this image here. This is a picture of these little balls, these crystals that I showed in the previous slide, in a range of sizes. And in fact, the reason that you're seeing these colors here, these are, by the way, these beakers are glowing. They're holding a black light over this slide and making these little beakers full of these solutions, these particles glowing. The reason they glow and the reason they give off light is because the little nanocrystal is absorbing the ultraviolet light and causing it to fluoresce, just like a Dayglow t-shirt would if you were, you know, at a party with black lights. But the unique thing about these materials is that they change color just based on their size. So if you look at the red beaker here, this has these quantum dot materials, cadmium selenide nanoparticles, and the diameter of those guys is about 6 nanometers. And if you change it, you make it smaller, you go down to 2 nanometers, then the color changes. And so this is a phenomenon that's also a nano phenomenon. The color, the glow in this case, completely derives from the size and not the composition. If you analyze these beakers, each one of these beakers has the exact same stuff in it, cadmium, selenium, and some water. So that's the key lesson from nano, that the real properties of a nanomaterial derive from its size. And so we would say the form determines the function, to coin a phrase from the architecture field. So what's the deal with the Braxane here? So why is this a nanomaterial? This is also a website that if you go to it, you won't be able to find any indication that there's nanotechnology there. Although if you dig down far enough into their website, you'll find this picture. This is what they say a Braxane is. And it turns out this is a nanoparticle. It's on the order of about 3-4 nanometers across. Or, sorry, no, this one's about 10-15 nanometers across. And it's made from albumin, which is just a normal protein that you have in your body. They cause it to fall out of a solution in a precipitate, and then they soak into it a conventional anti-cancer drug, paclitaxel. So this guy here, this is a molecule, and that's an anti-cancer drug. And so the formulation of a Braxane is an anti-cancer drug, but it's just stuck inside this nanoparticle. And the advantage of that, number one, the carrier for this drug is non-toxic, and it also degrades. But the key reason that works and why that nanoparticle works as opposed to just using the free drug is more or less illustrated in this picture here that I borrowed from another nanomaterial. And that is, if you look at the picture, this is a diagram of a tumor, an artist's conception of a tumor growing inside somebody's body. And this is a blood vessel feeding that tumor. It turns out that blood vessels are, they carry blood and they carry nutrients, and those things permeate through these blood vessels and feed the rest of the body, the tissues in the body. When a cancer grows in your body, it's growing very quickly, and the blood vessels are recruited by the tumor in a very rapid fashion. And turns out this kind of helter-skelter. the body is growing, this tumor is growing, and the body doesn't want it to be there, and the tumor just, all it's doing is trying to get bigger. And so it sends out these chemical messengers to tell the body to give it a blood supply. And it fools the body into growing blood vessels to feed it. And those blood vessels grow very quickly, and so they tend to be very, not very efficient, not very, not proper blood vessels. So they've got a lot of holes in them, and they leak. And so the reason these nanoparticles work is that these little guys, these nanoparticles, whatever they are, they tend to leak right through those holes in those blood vessels, whereas they wouldn't leak through the holes in a healthy blood vessel. And so the advantage of an abraxane kind of a drug is that the molecule itself, if we go back to our picture, if you just gave this drug to the patient, it would go everywhere into the body, and maybe it would hit the tumor and kill it. But the advantage of loading it into a nanoparticle is it'll float around in the bloodstream, and the drug doesn't do anything until it leaches out. And it doesn't leach out until this particle finds a home. And the particle naturally tends to accumulate in the tumor because, again, these blood vessels are so leaky. And so that's really how that works. It's a very simple process, really. It's just there's holes in the blood vessels, and these little nanoparticles can leak through. And so you can bring more of that anti-cancer agent to the place where you want it, where you want it to be treating. So one of the problems with quantum dots, and people have tried to use these quantum dots as these little glowing dots as treatment and imaging agents in the body. And one of the challenges they have in this field is trying to put these nanoparticles into the body causes them to fall apart. And unlike the paclitaxel, where the albumin, when it dissolves away, your body knows how to handle it because it's a non-toxic material, a quantum dot, when it degrades, it can actually be hazardous to the body. And so this more or less harkens back to my initial image that I showed you of our asbestos fibers. So if you're going to use a nanoparticle to deliver a drug, let's say, you don't want to use asbestos. Okay. Maybe it'll carry a drug and do what abraxane does, but once it's in the body, it may not go away. And so one of the key features of a nanomaterial, and the mantra for the people doing nanotechnology for medical applications, is that these medical devices have to go away. They have to dissolve, and the body has to be able to eliminate them. And that was really the challenge and the hazard with working with something that contains, say, cadmium. It might be, in this case, it is toxic to the liver. And so I'll give you one other example of nanomaterials that can solve that problem. This is work that actually a couple of high school students worked on this summer in my lab on these silicon-based nanoparticles. This is a beaker of these guys. They just look kind of pale yellow in solution. If you turn the lights out and put them under a black light, then they glow orange, and that allows us to see them and track them in the body, that color. This is what they look like, more or less. They're little nodules. They're all clustered together here in this picture. If you zoom in on one of these little clusters, these little balls here, you'll find very small holes. It's a porous material, and that's where we load our drugs. And this is an example of using a silicon-based nanomaterial to see a tumor. Okay, so we're not treating the tumor here like in that abraxane case. We're just doing an experiment to say, oh, where do these particles go? And this illustrates this concept of how a nanoparticle will accumulate in a tumor. So what you're looking at here is the back hind quarter of a mouse. That's his back leg there. Tail goes off this direction. And that little ball there is a tumor that was implanted and growing inside the animal's hip, or just above the hip, just below the hip, but just under the skin. And so what we did in this experiment is we injected these silicon nanoparticles into the tail vein, and they circulated through the bloodstream of the animal, and eventually they find their way into the tumor. And these three images here on the right just show you that. These are what we call false color images of the glowing, the fluorescence from that particle. So again, this orange glow here we're using as a diagnostic handle. We turn the lights off, we put the animal under a black light, and we look for glowing. And then we make a false color image here that just maps, tells us where the high intensity fluorescence is located. And you see that it finds its way into the tumor. And the hot spot here is right over where the tumor is. So these little nanoparticles, as we expect, nanoparticles can find tumors. But the important aspect of this experiment that the guys were working on a few years ago and then continued on into the summer is to look at how these things go away. And after 2 hours, the nanoparticles are in the tumor, but after 24 hours, you can see they've dissipated somewhat, they've broken up and started to dissolve. And that's really the key aspect that I want to get to with, and what really the big feature of nanotechnology in medicine is focused on, is making a material that can actually go away and be, as it degrades, it's no longer toxic. Let's see, how we doing? I got about 10 minutes for one more story. So this is kind of a, so if you weren't squeamish about seeing little mice on a table with tumors in them, how do you feel about poking a needle in your eye? This is a New York Times article. It was posted on the web a few years ago. This is from a company called Genentech. It's up in the Bay Area, and they make a drug for a disease called macular degeneration. Macular degeneration is a disease of the eye that generally it's age-related. When you get old, you go blind. It's one of the big 3 diseases that causes older people to go blind. Anybody know anybody who has macular degeneration? Turns out that if you're, there are a few of you up there, if you're over 40, over 50, you're pretty much, at risk of getting it. People who live to the 70s and 80s, almost all of them eventually get it. Sometimes it's pretty minor and you don't really notice it. In other cases, it can be a pretty aggressive disease and causes you to go blind pretty quickly. So how do they treat it? They can't cure it. And so if you give a drug to somebody, just a pill, there's no pill that works either, because there's a barrier called the blood-eye barrier that's very similar to the blood-brain barrier, and drugs can't get into the eye. And so this disease here is treated by this drug made by Genentech called Lucentis. And Lucentis is it's a protein-based drug. And what they found was that they have to inject this stuff directly into the eye of the patient every 6 weeks, and that's a typical treatment. So most patients, if they have this disease and it's an aggressive form of the disease, they're going into the clinic every 6 weeks to get an injection directly into their eye or both eyes. And so people don't like that. And so what these guys did is say, well, let's just crank the dose up. Let's give them a lot. Let's overdose. And if we put a big bolus of this drug in the eye, then maybe it'll take more like 8 weeks or 10 weeks or maybe a few months to clear out. And they had a problem when they did that. As they started ramping up the dose, then they got a couple of patients started getting strokes. Okay. So a few years ago, Bill Freeman, who's a medical doctor here at UCSD, approached me about this problem and said, hey, I've got patients coming in, they're getting this, we're treating them with this antibody-based drug, and I'd like to be able to put it inside something that'll just kind of like a sponge that'll soak up the drug and hold it in the eye for a longer period of time. And so that ended up resulting in this experiment you're looking at here. This is you're looking inside the eye of a live animal, a rabbit. You're looking through the iris, and so we're seeing what the eye doctor sees when they peek into your eyes to give you an eye exam. This is the back of the eye here. This is the optic nerve. The retina's back here, the part of the eye that does all the vision. And this is a needle track, and this is one of these little nanoparticles. This is a nanostructured particle. It's a little bit bigger than the nano, and it's got a little pretty green color to it. So I want to spend a minute or two talking about why it has that color, and this is the last example I'll give of nanotechnology to give us, how a nanostructure can give you a specific property. And we'll start with this picture here, these two objects. This, you guys probably know what this thing is, this shell up in the upper left-hand corner here. That's an abalone shell. It's actually a Paua shell. Anybody from New Zealand? Or here, we got friends from New Zealand. So Paua shell is fished out of the waters in New Zealand. You can get abalone everywhere, but these really intense blue and green colors from the shell generally come just from that area of the world. And so this is the material that they use for jewelry. Typically, if you have abalone shell kind of jewelry, they'll make it out of this Paua shell because it's so pretty. This little brick here is a calcium carbonate. And it turns out that that's the same material that shells are made out of. And so that's the formula down there. So why is it that the mineral calcium carbonate, when you dig it out of the ground, is this clear, transparent material, whereas the abalone shell, which is also made of calcium carbonate, has such intense color? Okay. And it's what the biologists refer to as a structural color. If you crack the shell open, you look inside, it's got these layers. And these layers, kind of the shell grows like a tree. Like trees have rings, the rings of a tree are in layers. And so the shells grow in layers. And these transparent layers, turns out that if they're the right spacing, in case of abalone, typically on the order of 300 nanometers, then they'll diffract light, and they cause light to diffract. Just like if you look at a CD or a DVD, you know how like there's grooves on those DVDs, that's how the computer reads them. If you look at the surface of a CD, it's got rainbows, right? You ever look at these things? You get pretty colors coming off of those things. Well, the DVD is just made out of clear plastic. So the color there you're seeing is also a diffraction phenomenon. So very similar to how the abalone shell gets its color. And the biologists refer to this as structural color because the color is coming from a structure, not from a pigment. So if you grind up the abalone shell, you'll get back to this crystal here. You'll just get some white powder. It won't have any color anymore. But if you leave it alone and you let it, you just look at it, then you have these layers, and these layers give you the color. Turns out that a lot of the iridescent colors, all the really intense colors in nature, usually are deriving from a structural color, what we call a photonic crystal. Okay. These materials can also be mimicked in the laboratory, and this is some work that we do in our lab. We make these little abalone shells out of silicon instead of out of calcium carbonate. And if you look at them close up, this is one of those chips that I showed on the previous slide. They have a specific color, but that color actually can change. This is an experiment where we took a chip and we just soaked ethanol on it, and that color changed. If you do this to an abalone shell, it won't change color. The reason this structure is changing color is because the layers here are porous. They're hollow. Let me skip over that. The structures are made and they're hollow, and because they're hollow, this shows again the banding, the layers of this silicon-based abalone shell. So very much like the abalone shell, it's grown in layers. This is the bottom of the chip. That's the top, and the light's going through there to give you the color. But this open structure here has holes in it, and those holes soak up that liquid and give you that color change. So let's see, we'll skip over that. And so in the end, you can make these little particles. Actually, I will show that movie. I think that might be easiest to see it this way. So how we make this nanostructure, this is an experiment that was done in my lab by a number of high school students this summer. We take these silicon wafers, we put them in a cell, we run some electric current through them. That causes this, the bubbling causes the structure on the silicon to become porous. And there we are now rinsing that porous structure off of the wafer. Here it's in a beaker, and we're running an ultrasound through it to make it into small particles. And ultimately those small particles can then be placed on a microscope, and we're looking at them here. And those particles, again, are this kind of spongy-like particles. And if we go through, there's another frame coming up here, which will be an electron microscope of these particles. This is what they look like, and if we zoom in close enough to them, we'll see that they have those pores. And so these are the particles that we use to inject into the rabbit eye. And why is that? What do we do with those? Again, they're particles. They have that photonic crystal color, and that's why they look green inside that rabbit's eye. But inside them, they have this pore, this sponge. And so we're placing drugs in that sponge. And the idea, again, is to focus on this macular degeneration problem where we'll put a drug in here and have it stay in the eye for a long time and have it leach out very slowly. The advantage of using the silicon carrier for that is it's very biocompatible and biodegradable. In other words, it breaks down and dissolves in the body. And also, if you make it small enough, you can inject it. Let's see. I think I'll skip over this. This just some data showing the drug being delivered, and I think we'll. And so the purpose of the color for these things, you might ask, why would you want to have a photonic structure in the eye? It's just going to, have colors to it, and it might interfere with your vision. And that was because Bill Freeman had this other requirement. He said, I don't not only do I want this particle to hold the drug and release it slowly in the patient's eye, I want to be able to look in their eye and see when the drug is all used up. And the advantage of that is that, you've got these patients, they tend to be old because it's age-related disease. They may forget to come back to the clinic. If you put this material into the eye, in some cases a patient may work out that drug in 6 weeks, but some patients may take 8 weeks. Drugs get metabolized at different rates in different patients. Every patient has a slightly different rate of absorption of that drug. And so they wanted to have some diagnostic tool they could use to look into the eye and see when it was time to give the patient another injection. And so the interesting aspect of these little photonic structures is that what you're looking at here is an experiment that actually Liz Wu did in my lab a couple years ago. She put these particles in a microscope stage and just watched them dissolve in water. And they started out with this pretty reddish color, and then as they dissolve, they turn green. And eventually they dissolve away completely, but as they dissolve, they change color. And that's because those layered structures are corroding away, dissolving away in the color. Just like in the abalone shell, the colors gently change as the layer gets thinner. And so that gave us a diagnostic. And so ultimately, this is what we were left with. We have this is a rabbit eye here. Has a little nanostructured particle in there. Now, the particles themselves are not nanoparticles. They're big, but the pores inside them are nanopores. And those are the ones that are important because that's what holds the drug. This is an example of a different kind of a drug loaded into these particles. And again, just showing that after the particles release the drug after 7 days, there's a change in the color that she could use to diagnose how much drug had been delivered to the eye. And this is actually just a correlation she drew between the color, you could read that axis as the color, and the amount of drug that came out of that particle. Okay. So that more or less finishes my story. We ended up with this example of using a nanostructure to be able to deliver, to use the nanoscale properties of material, in this case, to deliver a drug. Before that, we talked about how you can use a nanostructure or nanoparticle to specifically target or find certain special regions in the body. In the case of Abraxane, that would be a tumor. Because the features of this nanoparticle, the size of the nanoparticle is just right so that nanoparticle can be carried to a tumor and lodge itself in the tumor, where then the drug gets leached out and kills the tumor. And so those are examples of using the size of things to make things better. And this is maybe encapsulated best with this book. People, if you talk to any of the people working in nanotechnology long enough, eventually they'll, besides the Feynman lecture, they'll talk about seeing this movie, Fantastic Voyage, which was, Isaac Asimov wrote a novel called Fantastic Voyage, which was the novel associated with the movie that had Raquel Welch in it. She's a La Jolla High School graduate, and so we love her too, just like we like Dr. Seuss. So she's inside the submarine in this story, and the submarine is swimming around in some guy's body, and they use these laser beams to destroy this blood clot inside his brain. And so really this is the concept of taking something, making it small, and having it move through the body and do something. There's another aspect of nanotechnology that maybe is a little bit more current. This is Michael Crichton's book, Prey. It published just a couple years ago. The movie here is some of our nanoparticles that are seeking out their maker. Actually, this is the finger of Sean Mead, who actually made these particles. You can see they're swimming to daddy there. Anybody know how that was made? Anybody know how that movie was made? I'll give you a special prize for that one if somebody can figure out how to make them swim through that beaker, through that glass, and actually sense the finger and swim towards it. What? They're not magnetic. We do a lot of work with magnetic particles, but these are not magnetic. Yeah, over in the blue shirt. Electrostatic. So it's a parlor trick. Very good. So we took an electrostatic gun and we, charged up. And it's kind of like taking a balloon and rubbing it on your hair and sticking it to the ceiling. Same thing. And so he electrified the thing with one of these anti-static guns. And then as these particles are charged, they want to ground themselves, and so they go towards anything that's attached to ground, which is the human body and the guy standing on the floor. So let's see, I've got my own very own black light I'll give you for answering that question. So you too can make your own nanoparticles and measure them. All right, I should have pulled this out earlier, actually. They don't pull the lights down here, do they? Can you pull the lights down? You've got a keychain holder to it. So, all right, what you do is you push the button on top, and then it's like a little flashlight. Do we have a highlighter? Scribble on your paper a little bit. Scribble on your paper, and then you can go find the secret hidden messages with the black light. Now see if we can work the instrument. All right. Can you work it? Hold it up to the... So that's the phenomenon of photoluminescence we were talking about earlier. So that's the phenomenon of photoluminescence I was mentioning earlier, and as he's walking around the room. So what you want to do, that thing, if you push the button and hold it down, it'll actually slowly dim. So you just want to push the button once and then let go, and then it'll stay on for 10 seconds or so, and then it'll just power down. Then you just got to push the button again. Anybody have a tattoo? They're willing to show to the public. They'll glow a little bit. People with T-shirts on that have the bright day glow inks, you'll be able to see it. Okay. Also, anybody got any small brothers? Do you have any brothers or sisters, little kids? So I did this with this. You can go ahead and sit down now. I don't want to harass you too much because I want you to be sitting down before I tell you this story. So I took this black light to a grade school, and I had the kids play with the little highlighters, and then one kid came up and he shined the light on his pants, and his pants were all glowing right here. So that's the uric acid that So if you wet your pants, you can tell whether your brother or sister wet their pants because you shine that on their pants, you'll see it glow. You can also find out where the cat peed on your carpet with that thing. So the point of that lesson is that fluorescence, luminescent materials allow us to see things that we normally couldn't see. And that's why they use this fluorescence as a way to track, one example I gave you, tracking tumors inside the body. So this is kind of nanotechnology gone bad, right, where these particles have, if they were to get out, they would attack Sean and kill him maybe. That's the whole point of the story here. But probably both parts of that story have lessons to be learned. This is an example of this is a picture out of The Economist from about 10 years ago now. There was a mining disaster in the former Yugoslavia. They they were mining precious metals, and they had cyanide in these big leaching baths, and it spilled out and got into the Danube and killed all these fish. And the way they knew that there was something bad in the water, because all these dead fish started washing up to the shore. And so the lesson to be learned there is they didn't want the cyanide to get into the water, but it did. We didn't really care if asbestos got into our environment, or we had asbestos in our ceiling tiles. I mean, how bad could that be? I mean, you dig it out of the ground. I mean, how could that possibly be harmful to anybody? It's a mineral. And so there are materials that we are making today and that we have that can do bad things. And so one of the lessons and one of the rules of nanotechnology, in my opinion, is that no matter what you're making, it's going to be ending up in the environment, whether you like it to or not. And so these are my rules of nanorobotics. Anybody know of the iRobot series, Isaac Asimov? Yeah, some of you guys have read that. So these are those laws of nanorobots that I made up a couple of years ago. And so the first is it should not self-replicate. So these guys that are swimming around in the beaker there, I don't want them to start, doing what living things do, replicating themselves, because then they would even be worse. They'd be viruses. That's a little bit of a joke. The second, the structure must degrade. That is the important part, and that you really want it to fall apart. If it goes into the body as a medical device, if it goes onto your roof as a ceiling panel or as a solar panel, at some point that panel is going to be thrown into a trash bin somewhere and then go into a landfill. And so ultimately you want that material to degrade. And the products of that degradation should not be harmful. So you don't want to be making cyanide or something that breaks down into cyanide. You want it to break down into harmless products. Okay? And so that brings us all back to this lovely picture from Dr. Seuss. What's the importance of this last cat Z? Again, I call it nano because it's small, but it's not just small. And I hope you got this from my lecture today, is that the nanotechnology is just not about being small. It's that little cat Z has like eyes and nose and ears and hands, and it walks around. It has some function. It can do something. And so it's building a functional structure at that size. And having the structure be small but do something because of it being small, that is really the key to nanotechnology. And that's what Dr. Seuss figured out, and I think even he had the better idea than Feynman did, even though Feynman gets credit for it, and he's a brilliant physicist, and so everybody looks to him as our grandfather for nanotechnology, but I think it's Dr. Seuss. So that's the last. Okay, then finally then we leave with our last. I told you I'd tell about these nanomaterials. This is the last one. We really don't have anything to say about this. I mean, quite frankly, I don't know what nano gold does in a cold cream. I have a colleague who's a medical doctor and pharmacist in Montpellier, France. I visit him him and the other collaborators once a year or so. And he's been working with, he and his lab have been working with L'Oreal, a French cosmetic manufacturer, for decades. And he said, L'Oreal, I believe it was L'Oreal, I think that's the one. 25 years ago, they decided that, technology could be used as a marketing tool. And so unlike those other two devices I showed, the Gore-tex and the Abraxane, these guys, they don't hide it. I mean, they like, look, these are nanoparticles. And he said, the reason for that is if you go to, and you guys in the U.S. in particular, he said, you go to the U.S. and you guys don't want to drink any water that has anything in it other than pure water. You don't want any chemicals in your food. You don't want to wear any clothing that has some kind of coatings on it or anything that could be possibly some chemical or harmful. But if you go to a woman, and now this is not my opinion, this is my French collaborator's opinion. You go to a woman and you tell her, I will make you beautiful. She goes, okay, do whatever you can. And nanotechnology, no problem. And so that's why he says that they use this, they can use this in their advertising. In fact, this is true. L'Oreal decided to use technology, not nano, but 25 years ago, they decided to use technology as a marketing tool. And they developed a lot of liposome, a lot of nanoparticle work the early nanoparticle and a lot of nanotechnology work came out of the cosmetics industry because of that. It's kind of funny. So I'll leave you guys with that one, and just like to thank you for your attention. I'm happy to answer any questions.
Thank you very much for a very fascinating talk. We have time for maybe a couple of questions. Okay, yeah.
Hold on.
I was wondering if you knew if the particles that they injected in the rabbit's eye actually impaired the vision.
Yeah, the rabbits aren't talking, so we don't know. That's a little bit of a joke. It turns out that in the clinic, when I asked the same question to my eye doc guy, and I said, these particles have a color, you can see them, aren't they going to be a problem with the patient? And he said, no, we have a drug called Kenalog, for example, is one of the drugs they use in the eye today. It's a steroidal-based drug that's not water-soluble. And so when they inject it into the eye, it's like milk. It's a cloudy, powdery substance. And it's fine. He says the patients don't really notice that it's there. The reason being that the eye is focusing the light right on the retina. So if it's sitting inside the center part of the eye, just floating around in there, it'll scatter a little bit of light. You may get a little bit cloudy vision, but you don't really notice it because it's not in the focal plane. So that's presumably why you'd be able to do that. Also, these particles tend to settle at the bottom of the eye where there is no vision receptors anyway. Yeah.
Oh, sorry. I was kind of shocked to figure out that Dr. Seuss was the first one who conceptualized the concept of nanotechnology. But I have like two questions. They're quick ones though. When did they conceptualize the term nanotechnology, and exactly when did they start making the first projects having to do with that?
That's a good question. I mean, actually, Dr. Seuss, there's probably people before him who had ideas about making things small. And that's the one that I can find. The earliest product that I can see that I've been able to point to being a nanomaterial kind of purposely is the Gore-tex from 1985. However, if you go back, I just came from Italy last night, you go through some of these beautiful medieval churches in Europe and look at the stained glass windows, and those stained glass windows have nanotechnology in them. The reason that a lot of those intense colors show up in stained glass are because when they made the glass, there are some particles in there that turns out they're nanoparticles, and they scatter light in a specific way to give it that specific color. And so that's a nano thing. I mean, asbestos is a nanomaterial. It's just your key question is, when do people start recognizing, oh, this is a good thing. We want to make something in this size, and this is why, and have some beneficial properties. And that really is Feynman's lecture. I mean, I think when Feynman at least illustrated the scientific community the importance of doing that. I don't think he used the word nanotechnology or nano anything in his lecture. In fact, nano is just a prefix, right? It's a Greek prefix. It means 10 to the minus 9, as you all know, I'm sure. If you go back to the original Greek, the Greek nanos, translates as dwarf. And so most of the nanotechnology people don't realize this, working in this field. They just say, oh, well, we call it nano because it's roughly nanometer scale. Well, no, it's because it's small. And in fact, it's the original Greek meaning of the word nano. But if you want to look to where people started saying, okay, we need to be coining the term nanotechnology, and where it really became a field, you really have to go a few years after Feynman's lecture. You really go into the 1980s, before people started really doing things purposely to get nanoscale. Gore-tex was made that way because they recognized if they had small holes, it would do what I talked about. And so they didn't call it nanotechnology, and they still don't call it nanotechnology, but they were working in nanotechnology. And that's where you start seeing it emerge in the 80s. Yep.
Okay, I think let's thank the speaker again.